So welcome to this session 2 in this block 1, which is on exposure assessment and life cycle assessment. And if you go to the next slide, can I click slides myself? Yes. Yeah, here's the agenda for today's 1-hour session. So I will give a very brief introduction, mainly into the aims and the objectives of Working Group C. Then we have a very interesting presentation on extrapolation of exposure data, followed by one from Camilla on sharing of data. Then we have a presentation by Henk Goede on efficiency testing of risk management measures. And we end this session with a presentation by Nathan on life cycle thinking. Next slide, please. So to give you a very short introduction on Working Group C, because it was quite a large working group, we decided to subdivide the Working Group C into 4 subgroups. The main topic of today's session is mainly in Working Group C1, which is on human exposure and is chaired by myself. But there's also a working group on human hazard, Working Group C2. And then there's one on environmental exposure, Working Group C3, chaired by Klaus and Socko, and the 4th one is on eco-toxicology. So if you're not familiar with the working group structure, please visit the Nanosafety Cluster website if you haven't done so, and there you can find a full overview of what the working groups do, and also the possibility to sign up for the newsletter and the mailing list. So just in short, the Working Group C has several objectives, which is mainly overarching over the different projects in the Nanosafety Cluster. So it's there to encourage the sharing of project methods and techniques, as well as technical best practices to analyze and characterize nanomaterials. To encourage the sharing of project data, and Camilla will give a short presentation on that today. And of course, also the dissemination in collaboration with Working Group A, all the initiative that Martin takes, including this one today, is there to try and spread the word on exposure assessment and hazard assessment. So the current activities and plans that we have are ongoing. We have within the CEN NOAA mandate, we have a round-robin testing going on nanomaterial characterization by electron microscopy, as well as the testing of low-cost sensors to be able to detect nanoparticles. We contribute to the Malta project and various OECD activities to come up with technical guidelines. We stimulate the harmonization of data collection in collaboration with Working Group F on databases, and we develop and agree new research priorities within the EU. We have contributed and are still contributing to the US-EU collaborations, which are fit into the communities of research, in which we try to stimulate the joint activities between the US and the EU. And we have a similar dialogue with the Asia part, in which the nanoparticles are studied. We have discussions with the ECRs on the view of being involved in the direction of the working group. We try to interact towards the nano and microplastics fields, which seem to be an emerging field where we have our interest. And we transfer the knowledge that we have built in exposure assessment and hazard assessment into 2 new areas in the Nanosafety Cluster, which are the safe by design strategies is one, and nanorisk governance is the second. So you may note that the exposure and hazard assessment working group was very active in the beginning of the Nanosafety Cluster, in which all was to do on how to assess the exposure and the hazard of nanomaterials. But that was 20 years ago, and now we have really evolved in the new fields of safe by design and risk governance by keeping all the good work that we did in exposure and hazard assessment. So this was basically it for my very brief introduction, and I would like to introduce the first speaker, which is Remy Franken, my colleague from TNO, and he will give a presentation on extrapolation of exposure measurement data. So Martin, please, can you please change the slides? And Remy, the floor is yours.
A project we just completed called Extrapolating the Applicability of Worker Exposure Measurement Data, which is a fancy term for read across of exposure data. This project was a collaboration between TNO, HSE, Triskelion, and was funded by Cefic LRI. So currently in exposure assessment, the golden standard approach is still measuring exposure and is based on representative measurements. So what's representative? Meaning that you measure in multiple companies or multiple sites for multiple workers and repeated measurements per worker. In practice, the vast majority of exposure assessments are not done by measuring data, but since a single substance alone may require many exposure assessments due to all possible combinations which have an influence on exposure, and therefore exposure models were developed and play an important role to fill these data gaps. We differentiate between screening tools such as eStock TRA and higher tier models such as ART or Stoffer Manager. And the objectives of this project was to develop an approach which enables the use of existing measurement data more extensively than currently is being done. And it must be noted that this approach was developed for conventional chemicals, so not nanomaterials, but we'll come back later on how this might be useful for nanomaterials. So the idea was that you could apply corrections as necessary to account for differences between a source and a target scenario, where a source scenario in this case means an existing data set, and a target scenario is a user case scenario where no measurements are currently available. And the approach should be user-friendly. So we developed a hybrid modeling and measurement approach that can supplement existing exposure models. An estimate of exposure is based on existing measurement data from a similar source scenario, and what similar means, we'll come back to that later too. And then corrections can be applied to account for differences between existing data sets and a company situation where no data is available. And the approach is developed on the same theory of exposure determinants, which are used in models such as eStock TRA and ART. So it's a multi-step approach where one first would check the quality of the source data set he wants to use for the read across. Next, when the source data set is of sufficient quality, one would make an inventory or mapping of the differences for relevant read across parameters between the source and the target situation. Then in the next step, a statistical correction is applied to correct for the differences between the source dataset, and the uncertainty of the estimate is quantified. And well, again, the read across results are to be shown in a user-friendly way for users. So in step one, we make data quality check scheme, which I do not expect you can read, but it shows you that there are several questions with regards to the technical aspects of the data set, so sampling strategies, analytical methods used, and questions about contextual information available. So the exposure, well, is the substance well described, the concentrations in the product articles, are the activities well described, what's the scale, the duration, etc. And for if an answer is no to one of the questions, some alternatives are offered. So if the concentration is not known, for example, you might reasonably assume concentration. Then in the mapping approach, this is basically where you look at the differences between your situation and the data set which you want to use for extrapolation. So in this figure, you can see, let's say, for example, you have a target situation, both have toluene. In your case, you use a fraction of 20%. In the source data, it was pure. You want to use LAV. In the source data, there were no controls, etc., etc. And then when all the differences are mapped, we developed a small rule base which governs which extrapolations from the source to target is supported by the framework. So you can't take a random set and well, make all the extrapolations you need. And there needs to be a certain amount of similarity between the sets. Then you have your statistical correction, which is applied. So a read-across score is calculated by an algorithm which we developed. And the read-across scores take into account the emission potential, the dispersion factors, localized control, concentration, and the emission potential has been calibrated using a large data set. So a small correction has been applied on that. And if you follow that, you would get the final read-across score with your uncertainty quantified around that. So does it work? The theory which we described? Well, in 2 projects, we have tested the developed framework quite extensively. We have first developed 5 initial case studies on which we tested the framework, and these 5 case studies comprised of in total around 30 extrapolations. Then we made, based on those results, some refinements to the framework, and we fine-tuned it a bit. And then we added 5 additional more challenging case studies to test the refined read-across approach. So we used single sources and multiple target scenarios within each case study, and different ranges of activities and substance classes were studied. So gases, powders, volatiles, non-volatiles. We covered a very broad range of that. And in the figure, you can see the measured geometric mean from the source data set compared to the predicted geometric mean to the extrapolated data set. Normally, you wouldn't know these values, of course, because you don't have data there, but within the case studies, we did have measurements, and we extrapolated to scenarios where we could compare our predictions with the measurements in that set. So this has been developed for conventional chemicals. Would it work with nanomaterials? Since we are on a nano conference here, I don't know. I haven't tried it yet. Would I try it? I would first test the existing approach with a data set or case studies which contained exposure measurements to nanomaterials. And if that works, then the answer is, of course, simply yes, it would work for nanomaterials. If the results are not as promising, then probably some extra determinants need to be considered within the frameworks. For example, the particle size may be more of relevance for nanomaterials, aggregation or agglomeration. Maybe additional activities are not covered in the current framework, which uses procs or activity classes. Maybe different nano-specific exposure models can be used to underpin the read-across framework. We don't know. Current calculation is partly calibrated, so possibly the approach needs to be recalibrated on a data set with nanomaterials to make it more accurate. And as mentioned before, we use E-stock TRA and ART to underpin the rules of extrapolation. So maybe we need different models for that. And lastly, the thing we need to do is we develop the theory and we showed proof of concept of this theory, and it shows promising results. But we have mentioned user-friendly quite some time, and now the next step should also be to develop a user-friendly IT tool which can hold the IDs and the rules of this framework and makes it easier to work with. So in a nutshell, that was my presentation about read across. Thank you.
Thanks very much, Remy, and thanks for keeping it short. We're still a bit behind schedule, so I propose that we proceed. And please, again, to remind you, you can put questions in the chat, and the presenters are happy to answer them. So next presentation is by Henk Goede on the effectiveness and implementation of risk management measures. Henk, please go ahead.
Yes, thank you, Wouter. Can you hear me?
Yes, I can hear you. Okay, please try to present in 10 minutes also, if possible, Henk.
Yeah, all right, no problem. Thank you very much. Yes, I'll give you a presentation about the efficiency testing and implementation of risk management measures to mitigate exposure to nanomaterials. Just want to see if I can. All right. Just a moment. I just want to see if I can change this. I can't see my slides properly. Right, that's better. So just for introduction, as you all know, with the increasing use of nanomaterials, there's quite a need to ensure safe use in occupational settings. So this presentation will be about risk management measures in occupational settings. And so we're looking at mitigating and reducing exposure to nanomaterials using RMMs. So what do we need for risk assessment and modeling purposes? We need more information about the RMMs that can be used, or control measures that can be used in the workplace, and the criteria that's needed in terms of design of those control measures, and also the quantitative effectiveness of those controls. And in doing so, we can then better implement control measures in the workplace and provide recommendations on that. So there's been quite a number of projects that dealt with this topic, especially also in the US, for example, NIOSH, but also in the EU, like OECD and Life NanoRisk Sun Guide Nano projects. So there's a need to really integrate evidence that we do have on risk management measures and how to implement them, and provide guidance for that. And that's something that has already begun, and you do have some guidance at the moment, but not sufficient, and that needs to be upgraded in the future. Right, so just to give you an idea of, I wanted to explain a little bit more about why wouldn't we just use for example, the effectiveness values of risk management measures in occupational settings for conventional substances, and why would we bother to even look at nanomaterials specifically? Now, on the left-hand corner, you can see the typical pathways that's being used for in occupational settings or occupational hygiene. It's looking at the emission of a nanomaterial or a substance, the transmission, and then the emission towards the worker or towards a receptor. And along those different pathways, you have control measures such as for emission, process control or product modification. For transmission, you're looking at localized controls, dispersion controls, etc. And for emission, you're looking, for example, at respirators that are being used. I just want to use my pointer here. So on the right-hand corner, these are processes of nanomaterial mechanisms that you also have to consider. If you look at diffusion properties of nanomaterials, You can imagine that if there's in synthesis you have a release of a nanomaterial, along this way there will be coagulation, aggregation of nanoparticles, and that will also affect the effectiveness of different control measures. So that's something we have to consider here. On a more bird's eye view of prioritization of controls, what we distinguish typically is we're looking at the safe by material design approach. So you have the occupational hygiene hierarchy of using controls. So at the top of the pyramid, use elimination and substitution. So that's the most preferred way and the most effective way, obviously. What I'll be talking mostly about is the safe by process design. So then you're looking at engineering controls to control, for example, at the source or along the pathway all the way to the worker. And then the personal protective equipment, I'll also discuss that a little bit in this presentation. And later, in the last slide, I'll talk a little bit more about the safe material design. All right, this was meant to be shown with some. I'll just start talking about the more on the left-hand side here. I just want to indicate the differences in theory and practice, and how can we actually use information from, for example, intervention studies. If you look at engineering controls and protective equipment, if you look at the theory behind what is happening with nanomaterials, if they, for example, if you apply, for example, local exhaust ventilation, then you realize that the diffusion is a very important property that should be included, should be considered here, and the same for respirators, for the collection efficiency of filters. So if you consider the different theories around how effective nanomaterials will be, for example, extracted in a ventilation system, in this case will be from 200 to 300 will be quite effective, but smaller than that might still be effective if your ventilation system is strong enough to extract it. And it's interesting for respirators, for example, that your most penetrating particle size will be probably around 300 nanometers, whereas what's interesting is that in studies that's already been done is that very small particles sizes of, let's say, between 10 and 80 nanometer are very effectively being intercepted and collected in filter systems. But what we want to say here in this slide is that there's still insufficient information about how effective different control systems are. You cannot only use the theory behind it when you start doing tests. For example, the study shown here by Tai et al. For containment systems, you see there's quite a variation in the effectiveness of control measures.
You have 3 minutes left, Henk, so please try to speed up a bit.
All right. Right. So in terms of RMM testing, there's a lot of EU projects that dealt with this topic. And in most cases, you've got for RPE, for example, for respirators, they use a protection factor or a total inward leakage. For engineering controls, just a pre and a post test. So what we've done in the past is to convert all of that to a percentage of effectiveness of a control measure. And you can derive it from different studies, from varied experimental studies to cross-sectional studies by using models. And there's an upstream and downstream test for closing and respirators. So we've done a literature review on the effectiveness of control measures. This is just a slide showing the engineering controls. And our conclusion from the study was that we still do have very limited information about the effectiveness values of controls. Although what we found was engineering controls are very similar in the findings of the studies we on, for example, localized control, such as LEV systems, and respiratory protective equipment as well. Although you can see that filtering face pieces are often not very effective, or not effective enough for nanomaterials. So what have we done since then? We developed an exposed control library. It was part of a CEFIC LRI B153 project. So we added all this data in this database as well, so you can easily search for it, and you can find the database at this website. And you can search for different occupational and environmental RMMs actually. And I'll tell you a little bit more about the control measures for the occupational setting. So there's different sources in there, and one of the sources are specifically for nanomaterials. So just quickly going through the different screens or user interfaces you can find in eCell. You can search, for example, for nanomaterials and search for different types of control measures. For example, in this case, capturing hoods, containment, and enclosing hoods. Then you can first see which ones are the most effective, or what is the variability in the different control measures. If you choose one, for example, in this case, you choose fume cupboards, you can also select different records which are relevant in your case. You can go to eCard and find more information and see if it's relevant for your specific exposure scenario. And then when you select it, you can also do analysis and see how effective it is actually. And it gives you a median exposure level based on the records you selected, and also the variability, so that 95% high density interval.
1 minute, Henk.
Right. Right. So in terms of RMM effectiveness, I've already shown that to you. It's very important that it's ongoing research in this case, and we have to populate databases even more and get more information. I'm not going into details here, but this is also very important to include in RMM testing information and the study types that's being included for this kind of data. The variability is also very important. You can imagine that there's huge differences in control measures if you look at the technical specifications or the maintenance level of maintenance and the use in practice.
We need to wrap up. Henk, can you go to your concluding slides?
Yeah. So these are all interesting information about risk management measures, which is very important. So on our final slide, what we want to do is we want to bring together different, very important information about RMM applications and their effectiveness, and to improve guidance and implementation. So what we've done, we started with a project this year, Safe by Design for Nano. And we are on work package 4, which is Safe by Process Design. And what we want to do there is to develop a risk management measure performance prediction model, and link this also with the exposure model and infrastructure of the entire tool. What we also want to do, obviously, is to include Safe by material design, which will be work package 3 in the project. So I think that's something that will be developed coming year. Next year we will start off with most of these work packages. And these last 2 points are important things that we have to consider in terms of further analysis of RMM effectiveness data. And we also need to include much more data that we really need for the future.
Yep.
Okay.
Thanks very much, Henk.
Right.
Please put your questions in the chat again for the audience, and Henk, you can maybe answer them. We only have a short 10 minutes left for Nathan. So Nathan.
So sorry for the camera. I do not have any camera. My camera is not working, in fact. So Good morning, everybody. I would like first to thanks to Wouter and Martin for the great organization. So today we'll talk about life cycle thinking in nanoform release assessment, and I will use a gracious case study to develop my points. So I am Nathan Bossa, and thanks to Camilla, she presents like some really great work about the data template that we are building in Gracious in order to create, share, and reuse exposure data. And here I will more focus about how do we get this data experimentally and how these data are generated. So as you know, nanomaterial release of nanomaterial occur during their complete life cycle, from that synthesizing, manufacturing, use, and end of life. And since of 20 years, we are release library is growing. Now we are able to create, and we'll be able to reuse this data to other perspectives and to, for example, to create some model built on the top of it to predict the exposure. But what is important when we are trying to get the data, to get this release data, is to understand what parameters are driving the release. Meaning that how we can predict the release when we have one nanoform, one process is involved in the release. And for example, when this nanomaterial is incorporated in a product, how we can predict the release if we are doing if this product undergo abrasion. So, and this property, that is parameter that is driving the release, can be categorized in three main parts. Parameter linked to the processes, that can be the energy involved, etc. Parameter linked to the product where the nanomaterial is incorporated in, if it's the case, of course. And thirdly, the nanomaterial property, the nanoform property, if it's the size, the dustiness, etc. That can be some good parameter. And why we need this parameter and to understand the mechanism of release is to establish, in fact, hypotheses and professional criteria for grouping in order to provide some guiding principle for read across. As you know, we have like plenty of processes that can provoke some release, also plenty of different nanoform, and plenty of different application and product matrix that the nanomaterial are incorporated in. So we have plenty of possibility, and it's for that we need to define this parameter to perform some grouping. And these grouping are made of based on three different big data points. That's the release rate, how much is released, the release form, but also the exposure routes and population. So what can be these parameters? Parameter linked to the processes can be linked to the energy, the time. For example, the energy factor involved. You understand that, for example, if we are applying mechanical stress, we are applying high energy during a short period of time, and abrasion, and the aging factor will be mechanical stress. If we are dealing with weathering processes that could lead to some release, we are low energy, long period of time, and the aging factor are totally different. This is the rain and the UV. For the nano-enabled products, so most of the time, especially when we look at the release during use and end of life, we are dealing with nanoform that are incorporating in products, different type of products that can be solid matrices like paint, cement, also some liquid one and stuff like that. And so parameter linked to the product degradability will be sometimes some good driving parameter that could be some use for grouping. For example, you can imagine if you have one type of processes that is weathering, if you have a biodegradable polymer that contains some nanoform, we expect more release than if you have like some really strong and non-degradable polymer that incorporate nanoform. So it is this type of parameter that we are looking for with thinking of nano-enable parameter linked to the nano-enable project. For the property, we are looking for example, doing the synthesizing or the manufacturing. When we are handling nanoform, can be some dustiness that can drive the release of this nanoform. It can be the shape, the solubility as well. And so far, when we are compiling the data as a general view, the parameter linked to the processes are the most important parameter that drives the release. And for that, in Gracious, we have divided our work in terms of processes. For example, we have like some work that is targeting, if we want to group according to the mechanical stress, weathering, for example, washing of space type. We are trying to deal with, we are separating in processes. Then the parameters that drives that show the second less importance are linked to the nano-enabled product. For example, the product matrix degradability, but also where the nanoform localization. For example, if you have a coating, or this is embedded with a product. Also, the type of binding between the product and matrix and the nanoform. For example, in textile, when we are doing some washing, the binding time with the nanoform and the textile fiber is a really important parameter that can be used for grouping. And also, thirdly, the nanoform property, the shape, chemistry, and size. And we have seen that nanoform property modulates the degree of release, but it's not the first one. It's not the most, in most of the cases, it's not the most influence.
There's 2 minutes left, Nathan.
Okay, I will try to go fast. For example, in this case of paint can study, we are like, if you consider the life cycle stage of use, of paint can study, what type of process can undergo paint? You can go some weathering, abrasion. Also, you can think of your kids that is touching the paint, that's so smooth rubbing. So we have plenty of processes. Then if we consider of weathering, we have plenty of parameters that we could think that could be driving how much is released from paint during weathering. For example, it could be like the matrix from the nanoform property, the chemistry. Is it soluble or not? Is it the paint getting degraded by UV or rain? Do the paint is permeable or not? And is the nanoform applied at the surface or completely deep into it? Also the support of the paint. So this is what I want to point is like when you assess release, we need to have a really good understanding about the processes that is involved and also the product matrix, not only the nanoform property. So we need to have deep knowledge of how these products are made. So in Gracious, what we are doing, we are dealing with a different type of nanomaterial that we are putting in different type of product, paint, paper, plastic, and plastic film. And what is really important is we are working with industrial partners with relevant products that are actually commercialized. And so why is important to work with this type of product is because, in fact, we have the information from the manufacturer that we can go and ask them questions, have a good partnership with them to have information about the parameter coming from the processes or the product matrix that we are not expert at. We are more expert in nanoform characterization most of the time. But we need this deep knowledge in terms of product.
1 minute, please, Nathan.
Yeah, I go fast. I hope we'll be on time. So in Gracious, what we are simulating in terms of processes, we are looking for the use and end of life. And I will not go into details, but here is a type of diverse process that we are simulating, from food contact, abrasion, for end of life, landfilling, incineration, weathering as well, and a small dermal contact with smooth rubbing. For example, in the paint, we have seen bad effect of the paint that contain lead metals before with Saturnism, Saturnism disease. And so we are looking for this type of dermal contact, for example, in the paint. We are looking for the rate, form, and exposure and wood population. And shortly, what looks like experiment? In fact, what we are simulating experimentally these processes, and we are adapting some some method that has been developed by the industrial of the sector, some protocol that have been, to develop as a producer, to develop resistance. For example, in the simulating hand contact, we are this process, we use a crop meter, and this has been validated by the Consumer Product Safety Coalition to really extrapolate this data that we are getting from this experiment to a real life event. For landfilling, it's a bit more difficult because we need to extrapolate 30 years. Here we are using a protocol that takes 1 day basically. So we are applying worst case scenario, and it's difficult to extrapolate. But in that case, we are more comparing the results. And for weathering, we are using climatic chamber that simulates cycle of UV and rain, for example. And we use UV energy as a way to compare the experiment and to extrapolate to a life event. And we are collecting the runoff to detect how much is released, what is the form. And this
can you please wrap up now, Nathan?
Yeah. And thanks for your attention. I would like to thank you, everybody, all the partners involved and the organization.
Thanks very much, Nathan. And thank to all the presenters. Thank you all. I suppose the chat will remain open. So please put your questions in the chat. And I hand over to Martin now. Thank you.
Thank you, Wouter, and the team from TNO, and as well the team from Leitat for giving us these insights into many things that they do. And I guess we have to follow this up in more detail in dedicated sessions on exposure assessment, exposure determination, cross-linking or kind of extrapolating from other chemical exposure scenarios. I mean, there is a whole lot of things to be done, and I guess work group C is going to be in touch with working group A, that we can also kind of outreach this to the audience, that you can get access to this, to the application of these tools. So I give you again a couple of minutes for moving your bones and getting some fresh air into the head while I'm uploading the next presentations. And we are now looking forward to get into data, the data fairness, metadata discussion in a bit. Klaus Svensson is already here, the new chair, and we continue in 2 more minutes.